Hello, everyone. In science, and especially in chemistry, being very clear is extremely important. How do we describe what's happening in a reaction without causing any confusion at all? Well, today we're going to learn the proper way to write a chemical reaction, starting with simple sentences and then moving to the special language of symbols that chemists use all over the world.
So let's start with a very basic question. When you see a chemical change happening, how do you actually describe it to someone else? How would you write it down in your science notebook?
You might describe it in a full sentence, just like this one from our textbook. It says, when a magnesium ribbon is burnt in oxygen, it gets converted to magnesium oxide. Now, this is perfectly correct, but you have to agree, it's quite a long way to write it out, isn't it? A bit of a mouthful.
Surely there has to be a shorter, simpler way to write this. And yes, there is. The very first step towards making it simpler is something we call a word equation. A word equation takes that long sentence and makes it much, much clearer. See? We simply write the names of the substances involved, magnesium plus oxygen, and then we draw an arrow pointing to the new substance, which is magnesium oxide. This is so much shorter and so much easier to understand at a single glance.
Now, the substances that we start with, the ones on the left side of the arrow, they have a special name. We call them the reactants. So in our example, magnesium and oxygen are the reactants. Always remember, reactants are written on the left-hand side, or LHS. And what about the new substance that is formed at the end of the reaction? Well, that is called the product. Here, magnesium oxide is our product. And products are always written on the right-hand side, the RHS. So reactants on the left, products on the right. So there are a few simple rules, a sort of grammar for writing these word equations. First, you write your reactants on the left. If you have more than one reactants, you connect them with a plus sign. Then, you draw the arrow. This arrow is very important. It always points from the reactants towards the products, showing the direction of the change. And finally, you write your products on the right side. Simple. Okay, let's look at one more example, just to be sure we've understood this properly. When zinc metal reacts with sulfuric acid, it produces zinc sulfate and hydrogen gas. Now, just take a moment. Can you identify the reactants here? That's right. The reactants are zinc and sulfuric acid. And the products, of course, are zinc sulfate and hydrogen. See how neat and tidy this is? Now, word equations are a great start. But in chemistry, we can be even more precise and even more concise. So let's take the next step and start using chemical symbols and formula instead of full words.
As our textbook tells us, using chemical formula makes our equations even more useful. So instead of writing out the full name magnesium, we can just write its chemical symbol, which I hope you all remember is Mg. Here, you can see the difference so clearly. On the left, we have our word equation, and on the right, we have the chemical equation using symbols. We write Mg for magnesium, O2 for oxygen, and MgO for magnesium oxide. Just look how much shorter it is, and it actually contains more information. The formula O2 tells us not just that oxygen is reacting, but that two oxygen atoms are bonded together in a molecule. That's a level of detail the word equation just cannot give us. Okay, now, when we first write an equation using its symbols like this, we have a special name for it. We call it a skeletal chemical equation. You can think of it like, well, the basic skeleton of the final complete equation. It is correct, but something is still missing. It's not the full story yet. Let's look very closely at this equation again. Mg plus O2 goes to MgO. I want you to pause for a moment and actually count the atoms of each element. How many magnesium atoms are there on the left side, the reactant side, and how many are on the right, the product side? Now do the same thing for oxygen.
All right, have you counted? Let's check our counting together. For magnesium, that is Mg, we have one atom on the left and one atom on the right. Okay, that seems fine. But now look at oxygen. O. On the left side, in the O2 molecule, we have two atoms, but on the right side, in MgO, we only have one oxygen atom. They do not match. An equation like this, where the number of atoms of each element is not equal on both sides, is called a skeletal chemical equation. We can also say that it is an unbalanced equation. Now, this is a very, very crucial point, so please listen carefully. The word unbalanced does not mean the equation is wrong, not at all. It correctly shows us which substances are reacting. It just means the equation is not finished yet. It is an incomplete story.
So, if the skeletal equation is incomplete, what is the next step we must take to complete it? Well, that next step is called balancing, and it is absolutely essential in chemistry. Let's see why.
So, even though it's incomplete, a skeletal equation is very important. It serves a key purpose. It correctly identifies the reactants and the products for us, telling us exactly what substances are involved in the reaction. What it doesn't tell us, though, is how much of each substance is involved. It doesn't give us the correct proportions, or you could say the correct recipe for the reaction to happen. And this is exactly why it matters so much. I want you to recall from your previous classes a very fundamental law of nature, the law of conservation of mass. It simply states that in any chemical reaction, mass can neither be created nor destroyed. The total mass must always remain the same. So here is the most crucial point of all. If atoms are what make up mass, then the number of atoms of each element must be the same before and after the reaction. We started with 2 oxygen atoms on the left, so we must end with 2 oxygen atoms on the right. We cannot simply lose an atom along the way. Therefore, we must balance the skeletal equation to make it correct.
And this brings us to our final thought for today. Let's look at our equation one last time. We know that the atoms have to be equal on both sides. But we also know we can't change the chemical formula. We can't just change MgO to MgO2. So if atoms cannot be created or destroyed, what can we do to this equation to make it complete and correct? This is the central question of balancing equations, and we will explore the answer in our next lesson.